So yes, I will present one of the annexes with a higher number than what Peter just presented. So this is Annex 68 on high indoor air quality in low energy buildings. I have a number of subtasks that I will go through here. But first of all, why did we make this project that we started some 5 years ago? Well, first of all, to make very energy efficient buildings, net zero energy using buildings, they have to be super efficient and optimized. So also that would be necessary to look to the ventilation and to air tightness, also the topic that we just heard about from IBC. So it should be limited to what is necessary, not too little, of course, but just to the limit. So a minimal fresh air supply, it means that we'll go perhaps to the border of what could increase the risk of poor indoor air quality. You'll see on some of my slides the IAQ, indoor air quality as such. So our goal with the project was to achieve these comfortable and healthy indoor environments in buildings that are energy efficient. So going to the limit. I'm trying to shift here. So that makes an ideal balance that we should find between energy and efficiency and also that need for ventilation. So what we've done in the project, that's actually just one sentence that covers the whole thing in a nutshell, that we have gathered data, tools, and also some case studies to provide for practical use some guidances about this theme of ours. We are 15 countries participating in the project. We are 19 official organizations, but we have, when we are present in countries, also there are some other visitors. So altogether, as I note in the bottom of this slide, some almost 40 institutions have contributed over the 5 years to our work. We have some main activities. They are officially called subtasks, and I'll go through each of these in the next slides here. So first of all, a definition of indicators for indoor air quality and energy. What are the parameters that we are looking for and optimizing for? Second, we look to the pollutants that we have to be alert about in residential buildings. And that's, by the way, important to say that we are, for this work here, limited to residential buildings. Next, in the third activity, we are looking to modeling. It can be very complex. So what are the possibilities to make modeling about these phenomena we are dealing with? And then for the subtask 4, we become more practical. How can we bring this information into design practice and also into operation, and also looking to control strategies for systems in our buildings. And finally, we have collected a set of in-situ measurements and technologies for those, and also collected some more case studies. Let's go through that. In these slides, I have here on the subheader here, I have who is the subtask leader. So if you're interested in more details, perhaps I'm not so much expert into all of the details, but then you have a name whom to contact. But first of all, here to define the indicators we need, then we should identify some indices for the indoor air quality measures and to put them up in a quantitative manner. And then we would like to compare those also somehow, not forgetting, of course, that's very crucial to us, the energy. So always have an energy label next to some of the indoor air quality indicators, where we otherwise look to the pollutants. We set up some targets because there are so many potential pollutants, but which of them are, let's call it, the most interesting, and then make a set of metrics for those. So this was set up in a systematic way that could be somehow easy to get an overview about. And here's how it comes. We call it a dashboard, but we are looking to some groupings of the measures. So one is for long-term exposures. There are some exposure limit values for long-term exposures, and then each of these interesting pollutants we are looking to, many of them are VOCs, so volatile organic compounds, but also others like mold and particulate matter. But we listed them in a relative scale compared to the exposure limit. So that's why you see this red ring that kind of indicates the maximum permissible limit. That was for the short term, so for the long term, and then we have similar also a notion for the short term limits. And there's also the notion of disability-adjusted life years that is also very often used in literature. So that was also comprised in this set of 3 indicators for IAQ measures. And finally, as I said already, never forget about the energy, of course. So in this way, you can go with this dashboard and rate a building, how it performs. Second activity, we looked to the pollutants, new information that we gathered in the project about it. My colleague Jin was leading this subtask. So this was also doing some actual measurements. So some of the things, there has been already some information that we should say in literature and in research, but also some gaps of that. And we knew that there's a lot of interaction with thermal conditions and humidity, so we gathered new information on that experimentally, etc., and by collecting information from literature. So we had both some full-scale test chambers, like also you see in the background here, a room, but also laboratory test chambers were used to study emissions and sinks from building materials. We had also some small-scale chambers where we could study more the actual performances of individual materials. And then we tried to model that also to understand that, and we adopted a similarity approach I will present on my next slide, similar to how we are used to model other mass transports for materials also. And this was collected, some of the new information we got in a database. And we also made the notion of some reference buildings that could be defined nationally for buildings that were just living up to normal nowadays standards. And we defined some common exercises based on that things, 3 sets of common exercises we had. Here's a slide just to illustrate. Of course, I cannot go in details, but that's just an example of how when we vary temperature and humidity according to 3 different ways of doing so, we saw quite some influential effect of those variations. And that's exactly that kind of information that we achieved to identify in our project. Not for all combinations of materials and exposure variations, but just to indicate what kind of effects we could see. The similarity, we are quite used to modeling other phenomena for buildings, of course, all the thermal and energy-related things, also moisture we are nowadays quite good at. But could we then also bring some of that information into how we model emissions of chemical compounds from materials? I'll not go into details with this, but just to say that we can have a similarity factor between how is the emission of moisture, for instance, the blue part here, how that relates to emission of VOCs from a material. You may have a one-to-one relationship between how it's modeled. That's not always true, but therefore can we identify such a similarity factor for a set of materials and how which compounds that are being emitted from those. And we can see some patterns and mean that we can much more efficiently use information we have already from other knowledges we have, as I said, with moisture. Here's for one group of materials, another group of materials, and a third group of materials. So this constitutes to us a little database that we are making in this way. But of course, this is for future research to continue making much more of this information. Thirdly, we had the modeling activities led by Professor Grunewald from Dresden. So that was about gathering computational tools in this manner here, but make it possible to calculate this for whole buildings. So what are the simulation tools that are available? Also to identify, again, some reference cases and things that we could study and make some other common exercises to help each other to become good at modeling these things. A lot of tools are needed, and it cannot be one tool that does it all. So we have to have collaborations, if you will, between tools and what are their strengths and weaknesses, and where there's still some gaps, things we are not able to model, and how do we possibly cover for that as we can. Quality assurance is, I know it's a theme that's very much of interest to Professor Grunewald, so that's also, and of course, very relevant to make sure that whenever we model, that we know what we're doing, that it is good quality. Here's just a visual illustration of all that collection of rather advanced tools, each of them, but how can they collaborate to model these integrated phenomena for whole buildings? You recognize some building energy simulation tools, here's the tool that does the emission modeling, etc. Much of this set is a spring-off, you could say, from Annex 60 that was completed a couple of years ago, looking exactly to modeling of buildings. We had some reference cases. I've not talked much about this drawing, but many countries have the so-called passive cells from a very old nowadays European project. But this was used as a model for such a common exercise. So what would be the emissions of chemicals from a material under such controlled conditions as you could have in a chamber like this? A few of the participants in the project had physically these test cells, but otherwise this was a modeling exercise whereby you were able to model under certain thermal conditions what would be the airflow reality and what would be the emissions of the compounds from the source material that was positioned in the box. Now, practically, building design and control strategy was the fourth activity. So, Jakub Kulari, my colleague here in my university, conducted a bibliographic study of what is the reality, how do we cope with these advanced controls of ventilation, and what is legally permissible in different countries all over the world, at least from the participating countries, making interviews with stakeholders. And you see here a long list of who they would be, from architects and until public authorities regarding conditions and ambitions in this area. So that was one main group of their activities. Also, then was to make a collection of case studies and things that were kind of pushing the limits of how can we design and take into consideration in our controls of ventilation in buildings these pollutant patterns. And that became a rather exhaustive list. You'll see it on the next slide of case studies where these things were realized and gone through with these couple of sheets of information only, rather short, about these themes here. So first of all, for the design, what are the reservation requirements? What are the guidances? And what is current practice? That was for the first, from a previous slide, the interrogation, the questioning of people from practice and authorities in this area. And next, as I promised, a set of case studies. This list here has 24 case studies, examples of advanced developments done through the member countries. 16 of them are covering some design considerations, whereas the last 8 are considering more operational activities. I cannot read aloud all these here, but the slides, they will be disseminated, and then you can read for yourself afterwards more in detail what have they been. But as I said, they are all covered in a couple of pages in the main report from this subtask. The last subtask or last activity was an collection of in-situ measurements and case studies. And the first sub-activity in this was to simply look to experimental methods and make some technology assessment of how you can go and measure things. And next was then to collect who has done it in some control field test studies. Some of them were in individual rooms. Some of them were in real inhabited studios, so student rooms as it was, dormitories, and then for full occupied houses. So 3 levels of complexity, you can understand it as being. And lastly, in this subtask, they were collecting for a group of 7 examples of low energy buildings in different countries where they had made some rather advanced IAQ measurements and considerations also of these more unusual things with the pollutants in buildings. Yeah, some pictures from those. Perhaps they are not the most interesting here, but here's an example of how was done some different exposure studies and measuring the volatile organic compounds, and you can see which substances were followed here. So all this information is available afterwards. As I said, 7 case studies from different countries of energy efficient buildings, how were the results of indoor air quality studies, and also with the more advanced things. These are presented in such sheets here that are really working as indexes that you can get further information of all the specific measurements that were done. Finally, I should mention that we are now completing these days. I hope to have our final reports approved of the executive committee the day after tomorrow. So we are now ending this project, but there's going to be a follow-up project. We were Annex 68. A follow-up project will be Annex 86. It's just starting right now. It's in the preparation phase. Energy efficient IAQ management in residential buildings. And this new project will focus on practical and intelligent implementation of ventilation systems in residential buildings, again, by use of smart components and materials. So finally, we have from this project some reports. The first report came in 2017 and was co-published with IAVC and was about the metrics. And then we have 4 more reports from the other subtasks, which have been completed this year and are under approval by the executive committee. And we have in editing, we have a project summary report. It's going to be a 12-page report, which is under internal review here and will be published soon, we anticipate. Finally, I should mention that we have a homepage, and this homepage, it was live here this morning, so actually I think you can visit it even today. And I think that completes my talk. So thank you for listening, and this is my mail if you want to contact me. Thanks.